again, this example, one assumption that we made, which is kind of an important assumption, is that we said that the area that's available for conduction in the spreader is this full width, right? But in reality, you know, if you're a little unit of heat and you're moving through this this device, let's say you're over here on the corner, right? You're over here on the corner, and this whole thing is at the chip or the dielectric temperature. This whole thing is at the spreader. So you're going to want to start moving in this direction, right? You're going to want to move away from the heat. But let's see. But there's a resistance associated with that, right? You can't just move for free. So it's not possible to immediately have the full area available. At some point, maybe the heat can spread out and take up that full area. But this corner up here is likely to be, you know, pretty close to the ambient temperature or whatever. Like, it's not going to be participating fully in heat transfer. So we need to maybe bound the problem a little bit and understand what's happening here. So let's clear this off here. So there's kind of two limits that we can concern ourselves with. The first is to say that heat comes down and fully spreads immediately in this direction and then flows the full distance, right, with the full area available. So this is called the isothermal limit. Right? Isothermal maybe is obvious, but it's a constant temperature all the way across, and that's driving the resistance. The other limit is a case where, let's say, heat does not spread at all. Right? So you basically like chop off the ends of this, and then you have heat that just only flows straight down and never spreads out at all. And this is called the adiabatic limit. And adiabatic is just saying, okay, let's assume that these surfaces over here just don't participate at all. So it's adiabatic. So you can do both of the computations and see what the heat flow would be in each of these situations. We assume the isothermal limit, right? We assume the full area. Let's go back and just modify our calculations to look at the adiabatic limit and decide whether or not this temperature that we estimated is close or right. All right, so we can do that. Let's see, what would we need to do? So let's look at the resistances that depend on this area, which were what? The spreader, so this one here, convection, this one here. Those are the only ones that used the wrong area. So going back, we just say our conduction in the spreader is equal to thickness of the spreader over, instead of W squared S, it now is W squared C times KS. And then our convection, see, our convection to the water side is 1 over W squared C H bar W. So I'm modifying both the conduction, and then if the conduction is modified, then that means the only area that's participating is this bit here, and these others are not on convection. Okay, so we do that. We can go back, change our calculation, and that's what we're doing down here at the bottom. So I have the adiabatic model entered here. So again, I'm going back. Everything's the same except for I've now added in a conduction and convection modified resistance. I again need to guess. If I'm going through this process, I need to guess the adiabatic temperature, the resistance, and then calculate the energy balance again. Let me just see. Hopefully this works. Yep. All right. So what are we looking for? We're looking for the temperatures here. So now my new temperature is 141 degrees C, all right, where before it was 60-something, 69-ish. So, all right, I don't know if this is a problem or not, but it certainly is a lot hotter than the other one. And you might look at this and say, okay, well, my G dot was 5, and I assume that G dot corresponding to 80 degrees Celsius. Now that I know it's 141, my G dot becomes 10 instead of 5. right? And now the problem changes. So this, the assumptions that go into it, you have to kind of be careful to keep track of them. But if you look at this and say, I know that I can handle up to, say, 200 degrees C, no problem, right? And my G dot is valid for this temperature, no problem. Then you actually don't need to do anything more. Like, you don't need to go spend a huge amount of time building a complex 2D model, because you've just bounded the problem to be within these two limits. So you know you're safe within the limits, even though you don't exactly know the answer to whatever the temperature question is. You know that it's not going to be worse than that. So you just move on happily and focus your energy somewhere else, right? So this is a way of providing bounds on a problem using thermal resistances where you don't have to go into much more detail. Questions? Okay. All right, so let's do one more thing with this. I think we'll have time to get through this part. 5 more minutes. So let's take this idea of bounding the problem to like an extreme and see how far it goes. So we have a similar type of problem. We have hot side held at TH300 and a cold side held at 100. We have 2 different lengths that we're conducting through, or 2 different widths, I'll say, that we're conducting through. And we want to just kind of understand what is it that's governing the heat transfer in this problem, and what happens if we start changing the dimensions, the height dimensions here. Okay, let's see. So let's go through. All right, so we already know how to do the isothermal limit and the adiabatic limit. So let's just write those out. If we were to do isothermal limit, and we want to calculate the heat transfer rate Q dot in the isothermal limit, what is that going to be? Well, that's going to be Q dot, we'll call this Q dot iso, is equal to TH minus TC divided by R iso, where R iso is what? L1 over K H1 W plus L2 over K H2 W. Right? We're going in series, and we're adding each of the lengths with their corresponding areas. All right, if we do that and do the computation, we should see Q dot iso is equal to 6.67 watts. All right, you take my word for that, but you can look at the ease file as well. Okay, if we do the adiabatic limit, in the adiabatic limit, we have something similar, except our R adiabatic is equal to, let's see, L1 over K H1 W plus L2 over K what, right? K adiabatic limit, we're still going to be using H1. Right, so K H1 W. That leads to Q dot adiabatic of 3.33 watts. All right. So now if I'm just trying to bound the problem, again, I only want to know Q dot for some purpose. I look at this, I know it's, everything's okay, the value's above or below something I care about, I could be done with this. But the interesting thing, one interesting thing that can happen is somebody might say, and people actually have proposed this or used this as a model, is to say, well, what if I actually just took the average of these 2 heights, or took the average area that's available for conduction? There's a big complex problem, there's a whole bunch of areas available, and what if I just took the average and used that? All right, let's actually do that calculation for this, and you'll see maybe something surprising. So for the average area model, we would take our A bar is equal to the length of conduction, the total length of conduction over K times A bar, where A bar is equal to the length integral, the length average integral, 1 over L from 0 to L times A of x dx, right? So that's just the general way of integrating to find the average area. If we do that, let's see, what do we have? A bar is equal to 1 over L H1 WL1 plus H2 WL2. That's just our integral. And let's see, we then say Q dot A bar is equal to TH minus TC over R A bar. And that gives us 10 watts. What the hell? So these are the limits, right? These are the bounds on the problem. So how does that live outside the bounds? Well, it turns out that this restriction here, this restriction in area, is what's governing the problem. So if you start opening up that restriction in any way, the problem changes, right? The bounds on the problem change. So the average area model is not an accurate way of assessing heat transfer. Okay? We'll stop there. Again, I'm 1 minute over. Sorry for that. If you have any questions, I'll stick around, but we'll see you on Wednesday.